Hey guys, I'm Miuccamatics and welcome back to my YouTube channel Miuccamatics. If you like math related videos, do subscribe and hit the bell icon. Connected graph. An undirected graph is connected if there exists a path between any pair of vertices. That means between any two vertices there must be a path. A directed graph is connected if the undirected graph derived from it by ignoring the direction of edges is connected. So basically it's same as the above definition except we ignore the direction and check if it's connected or not. Remark: if a graph is not connected, then it is said to be disconnected. The connected pieces of a graph are called its components. A connected graph has one component. These are some examples of connected graphs. One component since it's connected, so this entire graph consists of one component. Now connected graphs, these graphs are connected because if you notice, now if you take any two vertices, any pair of vertices, say these two, we can form a path, so it would be just this edge. We want these a path between these two vertices, we can take this or even this as a path. This and this between these two vertices, we can go from here and go here, and there are many possibilities. As long as there exists a path between any two pair of vertices, it is called a connected graph. Now these are directed graphs, so we don't consider direction, though the direction is involved. We think of this as an undirected graph, and we check if there exists a path between any two pair of vertices. So say for example we want a path from here to here, we can consider this even though the direction does not permit us to do this, but it is allowed because of the definition. So this and this, so it could even take this as a path, though the direction is opposite, it is allowed as we assume it to be an undirected graph, same as in this example. Now these are some examples of disconnected graphs. Now if you notice, connected graphs basically mean there is no break in the structure basically, and disconnected graphs mean there is some break in the structure, as you can see here, over here, and there is a break. So now if you see in this example, there are three components, this and this. This is a graph consisting of four components. Note that vertex constitutes a component by itself. So these two vertices are two components, third component and the fourth component. So these are four components. Now this example, this is one component, the second, third, and this vertex by itself constitutes the fourth component. So this disconnected graph consists of four components. A theorem: in a graph with n vertices, if there exists a path between a pair of vertices, then there exists a path having less than n minus 1 edges between these two vertices. Now why n minus 1? The simplest possible path between two vertices will be just a single edge. So two vertices, one edge. Now say we have three vertices, so say these three, it will be two edges, or if you consider these three, two edges. Four vertices, three edges, and so on. Now the proof goes as follows. Let v1, v2, vn be the n vertices in the graph. Let vi1, vi2, vim be the path from vi1 to vim. We don't use v1, v2, vn, the notations, as it need not be from v1 to vn, it can take any order. So let vi1, vi2, vim be the path from vi1 to vim, two vertices, where vij's belong to v1, v2 up till vn. Now if some vertex is repeated in a path, that is vir equal to vis, where r is less than s, then by omitting vertices between vir and vis, we still get a path from vi1 to vim. Now what exactly does this mean? Omitting the vertices between vir to vis, where r is less than s. That means vir appears before vis. Consider this example. Now this is a path which we have v1, v4, v3, v2, v5, v3, V4, V5 and V6. So a path from V1 to V6. Now if you notice, V3 is repeated twice. So from V4 it goes to V3, V2, V5 and back to V3. So we can cut off this portion and just include just V3. So a shorter one would be V1, V4, V3, V4, V5, V6. Now again, V4, V3, V4 is repeated. V4 is repeated twice, so this path can be reduced further, and we get V1, V4, V5, V6. This is the simplest possible path. So that's what it means by omitting the vertices between VIR and VIS. We still get a path from VI1 to VIN. Now proceeding in this way, we remove all the repetitions of vertices in the path, just as I showed you in the figure. Hence the resulting path from VI1 to VIM has at most n vertices. Therefore this path has at most n minus 1 edges. As I showed you earlier, between 3 vertices there will be 2 edges. So between n vertices there will be n minus 1 edges. We say at most or maximum because we could have an edge directly from the first vertex to the last vertex, and that would be a shorter path. Another notation that can be used is let V1, V2, Vm be a path in a graph joining vertices V1 and Vm. If a vertex Vk is repeated in this path, then omitting vertices between the first appearance of Vk and last appearance of Vk, we get a path from V1 to Vm, in which Vk is not repeated. So that's how we can show the proof using this notation. The above proof can also be used for the following theorem. In a graph, if there exists a path from vertex V to vertex V prime, then there exists an elementary path from V to V prime. Now that path which we obtained, the simplest possible path, is basically an elementary path because we got rid of all the repeated vertices. Hence it's just the elementary path. So the proof is same as the previous, except the last part of the proof will not be included.